When we were together last, we were talking about how reactions happen, and that includes all issues like in what order do the bonds break and form, how fast do things happen, and what does the rate depend on. And we're viewing this from the perspective of a substitution reaction where a nucleophile, which is cyanide or Cn minus, ends up replacing a leaving group, which is I minus. And that's a classic example of a reaction type in organic chemistry that we will call substitution. And we had determined that you break the carbon iodide bond and you make the carbon-carbon bond. And if we were to compare bond strengths, we'd conclude that this reaction was favorable and downhill. But we want to know how it happens. And we were proposing a few mechanistic hypotheses. One was that you break the carbon iodide bond first to get an intermediate, and then afterwards you make the carbon-carbon bond. So if we were to propose an arrow-pushing mechanism for this process, showing the carbon iodide bond break first would look like this. Iodide leaves. Now, some of you may be wondering, how on earth does that happen? You'd predict, as we talked about, that that is uphill in energy because bond breaking is always unfavorable. And you can imagine this process happening if the carbon iodide bond has some fluctuation to it, some vibrational frequency, and if the molecule gets enough kinetic energy, the bond spring breaks and iodide flies off to wherever. And the transition state would look something like this, where there's a buildup of partial positive charge on the carbon and partial negative charge on the iodide. This is the intermediate. We would call that a carbocation. And again, I want to be real clear, this is just a hypothesis. We're not yet weighing in on whether this is true or not. We need to look at the data and make some predictions. Oh man, I got that thing going where you got to sneeze, but like it's just not happening. Okay, well, we'll do our best. Man, thought it was going to happen. All right. In any case, the second step would be to form the new carbon-carbon bond, and the transition state would look something like this, where there's partial negative on the cyanide, partial positive on the carbon, partial bond formation. This notation, by the way, with the brackets and the double dagger, that's how we talk about transition states. And then if we were to draw an energy diagram, we would predict that the first step would be most uphill because you're going from something that had bonds to something that doesn't. And the transition state between the starting material and the intermediate, we'll call that transition state 1, transition state 2. This first transition state is highest in energy. And the reason that matters is because, as you probably learned in general chemistry, the energy difference between your starting material and the highest energy transition state is your activation energy. We'll call this energy difference here delta G with a double dagger. You may have called it EA for activation energy in general chemistry, but this determines the rate. And in general, we will call the transition state that's highest in energy relative to, or the step that has the highest activation energy. Let me be clear about that. Highest activation energy step, we're going to call the rate determining step. Or I'll abbreviate that as RDS. But that's the one that matters for determining the rate. You'll notice that the activation energy for the second step is much smaller. So we might say delta G double dagger for step 1 is much bigger than delta G double dagger for step 2. meaning that the thing that is determining the rate is this first highest energy step, and then the step after that is much quicker. All right, does that sound vaguely familiar to you? You're used to thinking about that? When we talk about energy diagrams, somebody always wants to know, what if the first step has a really high activation energy, but the second step goes up even higher in energy? What is the kinetics for that? That starts to get a little bit more complicated. You can do the math for that, but we won't in the class, so you don't need to worry about that. Okay, let's talk about rate laws. You learned this a little bit in general chemistry, but a rate law takes the rate of a reaction and relates it to the concentrations of the things that are involved in the rate determining step. So for this reaction where we've said that the first step is, for this proposed mechanism, where we've said that the first step is the rate determining step, what should the rate law be? What molecules should appear in the rate law? Should Cn minus appear? No, because it's not participating in the first step, right? The first rate determining step, which we've decided is this one. So you would predict that the rate law for this reaction would be some constant, K, that's what the term we usually use for a rate constant. And it turns out you don't need to worry about this, but the rate constant is related to delta G double dagger. There's an equation that can take the activation energy and turn it into the rate constant. So the rate constant will be higher if delta G double dagger is lower. Okay. And then the other portion of the rate law is just going to be the concentration of methyl iodide, and that's it. Somebody always wants to know, how is it possible that changing the concentration of Cn minus wouldn't influence this reaction? Because of course, if you had no Cn minus at all, the reaction couldn't happen. And the answer is you're absolutely right. At really low concentrations of Cn minus, this rate law would not work anymore. And if you want to know more about that, you should take Chemistry 552, which in many, many years of teaching, there's like, some of you are like, no, not in a million years could you convince me to take that class. Okay, that's fine. It's out there. All right, this gives us a testable hypothesis, right? If this mechanism is real, if this is the way the reaction works, we would predict that changing the concentration of methyl iodide should change the rate of the reaction. So you could do an experiment, a kinetics experiment, where you change the concentration of methyl iodide and then measure the change in rate. And what do you predict based on that rate law? What should that plot look like? Linear, right? As you increase the concentration of methyl iodide, you should increase the reaction rate. And incidentally, if the plot here is linear, that indicates what we're going to call first order dependence on methyl iodide, or we'll say the reaction is first order in methyl iodide. What we mean by that is the exponent on this concentration term is 1, okay? So if we change the concentration and rate increases linearly, that's evidence for first order dependence on, and that tells you that one molecule of methyl iodide is involved in the transition state of the rate determining step. Now, tell me what we predict here if we change the concentration of Cn minus. Based on the rate law, you got a flat line, doesn't do anything, right? So if we saw this, if we measured the rate of the reaction and we changed Cn minus and nothing happened, we would call that zero order dependence on Cn minus. Okay? So all of this, you're seeing now that we can use a mechanistic hypothesis to make a prediction that we can then test and determine whether our mechanistic hypothesis is right. A mechanism like this one, where the leaving group leaves in the first step, and then only in the second step does the nucleophile come in, that mechanistic hypothesis is summarized by the following terms. We will call the reaction substitution, nucleophilic, meaning it's the nucleophile doing the substitution, unimolecular, which means there is one molecule in the rate determining step. Unimolecular is the same thing as saying zero or first order dependence on methyl iodide, zero order dependence on Cn minus. And we're going to abbreviate all of that with the summary SN1. So that's your first mechanistic hypothesis, SN1. There's one other piece of information that we might want to use to predict, to make a prediction for this reaction. And to do that, we actually need to change the reaction a little bit. So the experiment I'm going to propose is something that would not work for methyl iodide, and you'll see that in just a second. But you can use stereochemistry as an outcome that informs your mechanistic hypothesis. Wow, that was a long way of saying that. So let me give you another example. Suppose that you had a starting material like this, where your leaving group here, which is Br minus, is at a stereocenter, which I'm going to highlight in pink. You see that that's a stereocenter? Yeah? Okay. Now, let's make a prediction if the mechanism was SN1, which you will recall means leaving group leaves first. Then we get a carbocationic intermediate. And then here's Br minus that left. So tell me what you know about carbocations. What's the geometry at that carbon? Trigonal planar, right? Is that molecule chiral anymore? No, it's got no stereocenters, not chiral. So we've lost chirality in this reaction mechanism. Now tell me, what is the LUMO of this carbocationic intermediate? PTSD, that was an exam 1 question, but now you're seeing why we worried about it. It's what? Empty p orbital, right? And if we draw it from this perspective, that empty 2p orbital is above the plane of the page and below the plane of the page. And I'll draw it from the side as well so that you can see it. But now you'll see why we worried about what the LUMO was in the first place. Here is your carbocation. The empty p orbital looks like this. And, oops, I guess, yeah, fine. You can see now that in the second step, the step where the nucleophile comes in, and we won't worry about what that nucleophile is. This is just a prediction of the stereochemical outcome of the SN1 reaction mechanism. The nucleophile can attack the LUMO from either side, and either side is identical, so there can be no preference whatsoever for attacking from above or below in the second step. If you attack from above, you get this molecule. If you attack from below, you get its enantiomer. And because this has to happen, attack from above or below happens with equal frequency, and it has to be that way because the intermediate is not chiral, then what you get here is a racemate, a one-to-one mixture of enantiomers. So you can use stereochemistry as an indicator of whether you went through a carbocationic intermediate. If you start with a material that's chiral and you end up with a racemate, that's a pretty good indication that you had to go through a not chiral intermediate. So do you see this is a mechanistic test you could use? Use a chiral starting material, see what the product is. Does it still have, do you get an enantiomerically pure product, or do you get a racemate? And if you do get a racemate, that's an indication that you have to have gone through a non-chiral intermediate like this carbocation. Okay, questions about that? I know, I'm tired too. All right, so that's mechanistic hypothesis one. Let's do, yes, go ahead. Why does attacking from above or below change which enantiomer it is? The intermediate is not chiral. If you attack from above, you make the bond on this side. Now you do have a stereocenter. If you attack from below, you make the bond on the other side. Now you have the other configuration of the stereocenter. So if we don't know what the nucleophile is, we didn't say, but we could assign R versus S. You get the R enantiomer one way, the S enantiomer the other way. Yeah?
So is this just a way to verify if you have an SN1 reaction, more or less?
Yeah, a mechanistic outcome of an SN1 reaction is going to be you lose stereochemistry at the stereocenter where the leaving group was. Go ahead. Does carbon 2 flip based on where the nucleophile is? Yeah, this one? Yeah, the idea is because the intermediate was flat and planar, as the nucleophile comes in and makes the bond, the carbon where you make the bond is going to rehybridize from sp2 to sp3. Yep. Okay. Good. So that was the first mechanistic hypothesis, and I'm deliberately holding out to not tell you what the answer is because we need to consider the other mechanistic hypothesis. There are more than this, but these are the two that are pretty reasonable for this situation. So hypothesis 2 is going to be that we make the carbon CN sigma bond while, or if we want to be British, whilst the carbon iodide sigma bond is breaking. One thing we're not going to consider is forming the carbon sigma bond first and then the carbon iodide bond leaves. Any idea why we're not considering that? Break the octet rule. Yeah, we'd have to have too many bonds to carbon for that to be true. So let's think about this. What would it look like if we break the carbon iodide bond at the same time as the carbon nucleophile bond is forming? Presumably, we would, probably want to draw it different. Let's see. Presumably, if that happens, then the reaction is just one step, because the two things that have to happen at the same time. So here is the leaving group that has left. Let's imagine what the transition state would have to look like. So, I need a little bit of space. What do you think? There's actually a few options here. You could imagine a transition state where Cn minus comes in sort of from the same side as I minus is leaving from. And there might be a delta minus on Cn minus and a delta minus on I minus. So that's one possibility. We'll call this sort of same side attack. And then we'll put a double dagger there to indicate that this is a transition state. Then another possibility might be that Cn minus comes in 180 degrees opposite I minus. And we have a transition state that sort of looks like this, that iodide is leaving at the same time as Cn minus is coming in. So we would call, as opposed to same side attack, we would call that transition state sort of backside attack. Any ideas over which might be favored more and why? Go ahead.
Backside attack, because wouldn't that mean less steric, like torsional strain between the groups?
Backside attack, less strain between what groups?
The iodide and the cyanide.
Okay, so you're proposing that because the in the transition state, the I minus and the Cn minus, well, they both have partial negative charge on them, right? So you're proposing that that should be repulsive, and so keeping them as far apart as possible is probably the best bet. Okay, good. Other thoughts? Why? Go ahead.
Also, in addition to that, the hydrogens are a lot smaller than iodide, so I feel like just as far as how large the different constituents are, it would be more accessible for the cyanide to come in, quote unquote, from the left as it does on the second.
Okay, right. So you've got, you want to minimize repulsion between nucleophile and leaving group. The second thing you pointed out is there's less steric hindrance in backside attack because hydrogens are smaller, so you're coming in on the side where stuff is smaller, okay? There's one more factor that leans in the way of backside attack. It has to do with HOMO and LUMO. So tell me what the LUMO of methyl iodide is. What's the weakest what is the weakest bond between carbon and what it's bonded to? Didn't make any sense. The iodide, right? The carbon iodide bond is weaker. So the LUMO is the carbon iodide sigma star. We would put a node in between the carbon and the iodide. There would be small lobes pointing towards the node and large lobes pointing out on the other side of the node. We've already, because we know what happens in this reaction, we already know that the nucleophile attacks carbon. And if you're going to attack the LUMO at carbon, the best place to do that is where the sigma star is, which is on the backside. Okay? This is why we bothered to tell you about sigma stars in the first place. They point 180 degrees away from the bond that you're trying to break. So the other thing that tells you that backside attack is more reasonable is because that's where the LUMO is. Now, there is LUMO on iodide, but we've already dealt with the fact that we're not going to attack on iodide. There's two reasons for that. One is not a great reason, is the carbon's a little less electronegative than iodide, so you expect carbon to be a little bit electron poor. The other reason is if you do it this way, I minus gets to leave, and I minus is the conjugate base of a really strong acid. If you did it the other way and attacked iodide, the thing that would leave would be CH3 minus, which you know from our acid-base chapter is not very stable, really, really unstable, the conjugate base of a really, really weak acid. So the two arrows you would predict then are HOMO attacks LUMO, carbon attacks carbon, and in the same step, iodide-carbon bond breaks. Okay? Let's do an energy diagram. We said this is a single-step reaction, so the energy diagram is really easy. You have starting materials. We've said that products are more stable than starting materials, and we go through a single transition state. I am going to put the big X through this one. X is the Spanish name for the letter X. So I can say that and you're okay, all right. Except now it's all over the place. So let's just, So backside attack is preferred. We're gonna go through a single transition state. It's gonna be the one we drew above. And of course, this also has an activation energy. And that activation energy determines the rate of the reaction. Now, because there are two molecules involved in the rate determining step, the rate law for this mechanism would be rate equals rate constant, which again depends on this delta G double dagger. But then we're going to have two concentration terms in the rate law. One is for methyl iodide, one is for CN minus. We call this rate law second order overall because there are two concentration terms in it, and we call it first order in methyl iodide and also first order in CN minus. So now if we do those rate experiments, we predict that if we keep the concentration of CN minus constant, but increase the concentration of methyl iodide, we predict linear dependence. And if we measured the slope, that would give us the rate constant. Then if we changed and kept we kept methyl iodide constant, and then increase the amount of CN minus, we should also see linear dependence. And that linear dependence is consistent with first order in CN minus and first order in methyl iodide. Okay? Questions about that? Let's actually return to the issue of stereochemistry, because as I've said, you can use stereochemistry as an indicator of reaction mechanism. Let's just take that exact same chiral starting material. Oh, sorry. One more thing I gotta tell you. Just like above, we abbreviated the reaction as SN1. Because this reaction is second order overall, it's got two concentration terms in the rate law. We will call this substitution nucleophilic, because the nucleophile is the thing that's swapping itself in, and then bimolecular, because it's second order overall, and we will abbreviate that as SN2. Okay, so that's a second mechanistic hypothesis. Let's imagine if the reaction mechanism were SN2, let's imagine what the stereochemical outcome has to be. We start out with something that's chiral. We know that we don't go through a planar carbocationic intermediate, and we know that Cn minus replaces I minus from the other side. So what do we predict the stereochemical outcome should be? Let's just imagine a generic nucleophile. Br minus is the leaving group. The SN2 reaction mechanism is going to involve attack from the backside, and Br minus leaves. What is the stereochemical outcome? So this can be hard to visualize, so it might be useful to draw this molecule from a slightly different perspective. I'm going to draw the carbon here. Can I do this? Probably not. Well, we'll do our best. So this is the molecule viewed from a slightly different perspective. Here is the nucleophile coming in from the back side. Here is Br minus leaving. We would see as that happens that the nucleophile ends up on the opposite side of the molecule as the Br minus did originally. And the reason for that is, as the reaction proceeds, we go through this transition state where Br minus is leaving and the nucleophile is coming in. And it's like almost along the way, the carbon in the middle rehybridizes to become planar, sort of sp2 hybridized-ish, and then Br leaves and nucleophile comes in from the other side. And as the nucleophile is coming in from the other side, it repels the groups on the carbon and pushes them to the right. We call that outcome inversion of stereochemistry. And it is an outcome that's always associated with SN2. Now, I've drawn the molecule, again, slightly different so you can actually see the inversion happening. But if we were to draw what it looks like from the same perspective as above, the product would have the nucleophile attached to the same carbon, but now a dash instead of a wedge. How did the proton, which used to be a dash, become a wedge? Well, the nucleophile pushed it up, almost like an umbrella popping itself inside out. All right, so inversion of stereochemistry is a consequence of the SN2 reaction. So you got multiple tools. You can do the kinetic experiment, or you can do the stereochemical experiment. Go ahead.
How is inversion of stereochemistry only associated with SN2 and not SN1?
With SN1, the reason that inversion of stereochemistry is only associated with SN2 is because rather than get a one-to-one mixture, this is 100%. In other words, your starting material was chiral, your product is chiral and is a pure enantiomer for SN2. For SN1, your starting material is chiral, your product is a one-to-one mixture. The reason that happens for SN1 is you go through this planar intermediate where there is no preference at all between whether you attack from the top or the bottom. Whereas in SN2, there is 100% preference to attack from the backside. Yes?
Remind me how you decided the first one was unimolecular and this one.
Yeah, the term unimolecular versus bimolecular refers to the rate law. How many molecules are in the rate law? How many concentration terms are in the rate law? For SN2, there are 2 of them, so it's bimolecular. Another way of interpreting that is to say the rate determining step involves 2 molecules. For the SN1 mechanistic hypothesis, the rate determining step only involved one molecule. There was only one molecule in the rate law, so that's where unimolecular comes from. Okay, good. Others? Yes?
Can you explain how the intermediate state in this last one that we did causes it to have?
Yeah, so this transition state, which is a high energy maximum, how does this cause it to have inversion? Well, there's two things that cause this to have inversion of stereochemistry. The first is backside attack. And that may actually be the only thing. The nucleophile has to come in from the opposite side from where the leaving group is leaving. As that happens, you imagine this group leaving, this group coming in. The electrons on the nucleophile are going to start to repel the electrons in the carbon-carbon and carbon-hydrogen bonds here. You'll get to an intermediate state, a transition state rather, that looks like this, where everything's sort of flat. And then as the leaving group continues to leave to the right and the nucleophile comes in from the left, that will start to push these groups to the right, and that's where they end up over here. Yep, no?
Is the backside attack always advantageous?
Is the backside attack always advantageous as opposed to what?
Same side?
For the SN2 reaction, backside attack is favorable for three reasons. First, it minimizes electron repulsion between the nucleophile and the leaving group. Second, there's less steric hindrance to do that as opposed to come in from the front side because the leaving group is larger than the hydrogens. And finally, and perhaps most importantly, that's where the LUMO is in the first place. And reactions happen when HOMO attacks LUMO. So knowing where the LUMO is can tell you where you attack the molecule.
Okay, so it's for the same reason. I guess I don't understand why that is flat in transition state.
Let's see, we needed an SN2 animation, which I don't have. So if you Google that and watch a video on YouTube, there will be animations that show you how this process happens. Yeah, I'm sorry not to have a better demonstration. Yes?
Is there ever a situation in which same-side attack is more favorable?
Is there ever situations where same side attack is more favorable? Organic chemists have made an industry out of like probing mechanism and exceptions and stuff. For our purposes, we're going to assume if the mechanism is SN2, there's going to be backside attack. I'm certain there are exceptions that I'm unaware of. Yeah. Okay, so ready for the big reveal? We've got two mechanistic hypotheses. It turns out for this combination of nucleophile and electrophile, the mechanism is SN2. So we'll highlight this one green. For this, and I'll just write it up here, the correct mechanism for this reaction, if you did those rate experiments, would be SN2. That is, negative charge on the carbon attacks the carbon of methyl iodide, and iodide leaves all in the same step. But as you've seen, both reaction rates for SN1 and SN2 depend on the structure of the molecule that has the leaving group. So we're going to learn some things about this electrophile that will bias the mechanism towards SN1 versus SN2. And we're also going to learn some things about the nucleophile, because the rate law for SN2 depends not only on the electrophile, but also on the nucleophile. So we're going to learn some things about the nucleophile that will help us understand whether the reaction proceeds via SN1 versus SN2. Okay? Questions about that? All right, before we do that, I have to tell you something that you're not going to need to worry about until chapter 8. Okay? But full disclosure means that I want you to be anticipating this because the world's about to get a lot more complicated. You're going to learn in chapter 8 that in addition to substitution reactions, there's another class of reactions that has been competing with substitution reactions the whole time, and that we oversimplified to you and didn't tell you about it earlier on. And that's probably a decent decision in terms of teaching, but I always like to, full disclosure, at least at the beginning. So, should we do this? Yeah, why not? So I'm going to show you in Spartan. Whoa, not that. I'm going to show you in Spartan a molecule let's just get rid of one of those methyl groups probably. That's fine. All right. This is 2-bromopropane. The bromo is sort of this dark red color. You can see the carbon-bromine bond is long. If I download the details from the online database, I can show you the LUMO. Now, before I do that, you would have predicted that the LUMO was what for this molecule? The sigma star, right? So just so you can expect where to see the LUMO. On this image, you would expect there to be a node in between the two atoms, the carbon and the bromide. You'd expect some LUMO to be on the bromine, but most of the LUMO to be on the carbon and pointing 180 degrees away from the carbon-bromine bond. Okay, that's what you expect. You ready for reality? Gasp. You can see from this image that the LUMO is mostly what you see, what you would expect. You have a node in between the carbon and the bromine. There is a node at the bromine and a node at carbon. That's true for all hybridized orbitals. You see smaller lobes pointing towards the node, larger lobes pointing away. But the thing that's unusual and new here is that some LUMO is on the adjacent hydrogens. Okay? Why? So that's something we need to talk about. And the reason why is a concept called hyperconjugation. Okay? So let's talk about that briefly. But you can see now why this is important. Because if a nucleophile looks at this molecule, there are now multiple places it can attack. A nucleophile can attack the sigma star at the carbon, or it can attack at the adjacent hydrogens. And there's going to be different outcomes depending on where the nucleophile attacks. So let's try to explain that real briefly. Here is the carbon bromine bond. Here are the adjacent carbon, here are the carbon-carbon bonds. We'll call this carbon that's attached to the bromine the alpha carbon, and we'll call these carbons that are adjacent to the alpha carbon the beta carbons. And I'm going to draw in the carbon-hydrogen bonds for the beta carbon. Here is the node between the bromines. Here is the sigma star, smaller lobes pointing towards the node, larger lobes pointing away from the node. And this is what you saw on the Spartan image. Okay, so this is the empty sigma star between the carbon and the bromine. The concept of hyperconjugation refers to overlap in a molecule of a filled orbital, and usually that's a bond or a lone pair with an empty orbital. And that empty orbital could either be a p orbital or a pi star orbital or a sigma star. And in this case, it's the sigma star. And hyperconjugation works. This overlap is always side-by-side overlap. Okay? So when an orbital, and I should be clear, the filled orbital has to be adjacent to the empty orbital. That means one bond away. All right, so the filled orbitals that overlap with the sigma star are these adjacent filled carbon-hydrogen sigma bonding orbitals. All right, and we'll draw them like this. Okay. So when hyperconjugation happens, here are the consequences. There are two of them. The electrons in the filled carbon-hydrogen sigma bonding orbitals spread out a little bit toward the empty orbital. And the second consequence is, and remember, delocalization is favorable. The second consequence is that the LUMO, the carbon-bromine sigma star, spreads out onto the adjacent hydrogens. Okay? So if you can understand those two things, you already know enough. The LUMO spreads out a little bit onto the adjacent hydrogens. Some of you are going to be uncomfortable with the filled orbital overlapping with an empty orbital. You're going to say, I thought you told me that when you fill a sigma star, the bond breaks. And that's true, but this is not complete filling of the sigma star. This is just a little bit of sharing. Okay? Complete filling of the sigma star would look like this. The hydrogen is now just on its own. There's now a pi bond there and Br minus left, right? That's not what's happening with hyperconjugation. Instead, the electrons in the carbon-hydrogen bond are spreading out a little bit in space towards the LUMO, and then the LUMO is going to spread out a little bit in space towards the hydrogens. A second thing, if you're watching really carefully, that's going to make you uncomfortable is why the LUMO lobes on the hydrogens are red instead of blue. There is a reason for that, but I'm pretty sure you don't want to know it. If you want to know it, come talk to me, I'll tell you. Okay? But you can just not worry about it. Yeah, go ahead.
I think I kind of forgot my question.
Okay.
I was going to say, I think it was like, if you have, oh, okay, yeah, if a LUMO is unoccupied, then how come some of the electrons, do you call it unoccupied when the electrons are shared?
So if the LUMO is unoccupied and there's a little bit of delocalization into the LUMO, then is it now not the LUMO anymore? No, it's still there and it's still empty. If you want a more detailed explanation, I can provide it. Yeah.
This is about the end of last class. We didn't go over this. Are we expecting that on the test?